Hi everyone. This video is to present our ICCV 2023 oral paper on the robustness of open world test time training, self-training with dynamic prototype expansion. Before we dive into the details of our research, let's talk about the motivation behind it. Test time training adapts pre-trained model to OOD target domain during the online inference phase. Existing approach often focus on improving test time training performance under well-curated target domain data, only covariate shift. In this work, we propose the open world test time training OWTTT, considering both covariate shift as weak OOD and semantic shift as strong OOD in the target domain. We first empirically evaluate existing TTT methods and reveal that methods through self-training and distribution alignment would all suffer, both of that unable to distinguish and reject strong OOD, which cause potential risk. This is an overview of the proposed method for open world test time training when applying the source model to the open world scenario. Testing data may be contaminated with strong OOD samples. We first peel out potential strong OOD samples by dynamic optimal threshold tau star for inference. Then we expand the prototype pool by isolating strong OOD samples and updating model weights through prototype clustering and distribution alignment. It is unreasonable to use a predefined threshold in test time training. Instead, we developed a hyperparameter-free approach to pure out strong OOD. We defined a strong OOD score OS for each testing samples as the highest similarity to source domain prototypes. We make an observation that the outlier score is subject to a bimodule distribution. So the problem can be formulated as dividing the outlier score into two clusters, and the optimal threshold will minimize the intra-cluster variation. We further define an extended strong OOD score OS for each testing samples as the highest similarity to both source and the target domain prototype. A similar method is used to determine the samples to expand prototype pool. With additional strong OOD prototypes, we define the prototype clustering laws for testing sample, making them embedding closer to target prototype and kept away from others. We adopt an evaluation metric similar to open world classification tasks, choosing the accuracy of the weak OOD samples ACCS, the accuracy of strong OOD samples ACCN, and the harmonic mean ACCH between ACCS and ACCN. Following the prior works, we first evaluate open world test time training under noise corrupted target domain with CIFAR 10C, CIFAR 100C, and ImageNet-C datasets. Further, we introduce random noise, NNIST, SVHN, Tiny ImageNet as strong OOD testing samples. Our method outperformed all other methods. We further evaluate Vista C and ImageNet R to demonstrate the effectiveness in the style transfer target domain. Our method consistently outperformed the competing method during the whole test time training procedure, and the performance gets progressively better as the number of test samples increase. We further present GSNE visualization at 4 different stages. It is obvious that different semantic class as colorful dots become better separated as TTT progresses, and the strong OOD samples as black dots are always well separated from weak OOD samples. In conclusion, our paper has provided valuable insights into test time training. We argue that open world test time training can be spoiled by strong OOD testing data. So we introduce a baseline method by prototype clustering with distribution alignment regularization, a strong OOD detector, and prototype expansion. Further, we establish a benchmark and our approach achieves state-of-the-art performance. Thanks for listening. You can scan the QR code to learn more about this paper.